Windows operating system is a multi-threaded kernel that provides support for real-time application and multiprocessors. On uniprocessor system, Windows provides interrupt masks to protect access to global resources. It protects access to global resources using spin lock. A spin lock is a lock that causes a thread trying to acquire it to simply wait in a loop, like a spin, while repeatedly checking whether the lock is available. Since the thread remains active but is not performing a useful task, the use of such lock is a kind of busy waiting. The kernel uses spin locks only to protect short code segments, like a Solaris. The kernel ensures that while holding a spin lock, a thread will never be preempted. Windows provides dispatcher object for thread synchronization according to several different mechanisms, including mutexes, semaphores, events, and timers. The system protects shared data by requiring a thread to gain ownership of a mutex for accessing the data, and when it is finished, release the ownership. Events acts like a conditional variable to notify a waiting thread when desired condition occurs. The timers are used to notify one or more threads when time expired. Dispatcher objects may be either signaled state or a non-signaled state. Signaled state indicates that an object is available and the thread will not block when acquiring the object. Non-signaled state indicates that an object is not available and the thread will block when trying to acquire the object. This figure illustrates the state transitions of a mutex lock dispatcher object. When the owner thread releases mutex lock, the state becomes signaled, which means the object is available and the thread will not block when acquiring this object. After a thread acquires this mutex lock, the object becomes non-signal state, which means the object is not available and the thread will block when attempting to acquire this object. Linux provides several different mechanisms for synchronization. For the semaphore, when some process is trying to access semaphore which is not available, semaphore puts process on wait queue, FIFO, first in first out, and puts task on sleep. That is why semaphore is known as a sleeping lock. After this processor is free to jump to other task which is not requiring this semaphore. As soon as semaphore gets available, one of tasks from wait queue is invoked. There are two flavors of semaphore is present, basic semaphore and the read-writer semaphore. Spin lock is a special type of a synchronization mechanism which is preferable to use in multiprocessor SMP system. Basically, it's a busy wait locking mechanism until the lock is available. In case of an unavailability of lock, it keeps thread in light loop and keep checking the availability of lock. Spin lock is not recommended to use in a single process system. On single CPU system, spin locks replaced by enabling and disabling kernel preemption. Atomic operation is a very simple approach to avoid the race condition or deadlock. Atomic operations are operations like add and subtract, which perform in one clock cycle. And it's an uninterruptible operation. The atomic integer methods operate on a special data type, atomic_t. A common use of the atomic integer operations is to implement counters, which is updated by multiple threads. Atomic_set is to set the counter with the parameter. So here, example, we set the counter to 5. Atomic add is to add the first parameter to the counter, so the counter equals the counter plus 10. Atomic sub is to subtract from the counter. So in this example, the counter equals counter minus 4. Atomic increment is to increment value of the variable. So just like I++. So counter equals counter plus 1. Atomic read automatically read and return the value. So in this example, it return the value in the counter. POSIX API is available for programmers at the user level and is not part of any particular operating system kernel. Of course, it must be implemented using tools provided by the host operating system. In this section, we will cover mutex locks, semaphores, and the conditional variables that are available in pthreads and the POSIX APIs. These APIs are widely used for thread creation and synchronization by developers on Unix, Linux, and the Mac operating system. POSIX thread library provides implementation of the mutex primitive used for mutual exclusion. Mutex is created using pthread mutex init and disjoined using pthread mutex disjoin. Obtaining a mutex can be done using pthread mutex lock or try-lock function, depending on if the timeout is desired. And the releasing a mutex is done by pthread mutex unlock. There are two types of POSIX semaphores, named and unnamed. As the terminology suggests, named semaphores have a name. Named semaphores can be used by unrelated process. Unnamed cannot. Named semaphores are shared by several processes. Named semaphores have an owner user ID, group ID, and the protection mode. By using sem_open, you can create a named semaphore that has a name defined in the file system namespace. An unnamed semaphore doesn't have a name. Instead, the semaphore is placed in a region of memory that is shared between multiple threads or processes. Since POSIX is typically used in C, C++, and these languages don't provide a monitor, so POSIX condition variables are associated with a POSIX mutex lock to provide a mutual exclusion. The following code creates and initializes a condition variable as well as its associated mutex lock. Java language and its API have provided rich support for thread synchronization. In this section, we will talk about Java monitors, reentrant locks, semaphores, and the condition variable. Let's first take a look at a Java monitor. In this example, we have a class called bounded buffer. And in the first part is the private data part. Then we have the constructor, public bounded buffer. This method has the same name as the class name, though this is the constructor. Then after the constructor, we have two methods. One method is called insert. Another method is called remove. And we note that the synchronized keywords, those are synchronized methods. Invoking a synchronized method requires owning the lock on an object instance of bounded buffer. So if the lock is already owned by another thread, the thread calling the synchronized method blocks and is placed in the entry set for the object's lock. The entry set represents the set of threads waiting for the lock to become available. If the lock is available when the synchronized method is called, the calling method becomes the owner of the object's lock and can enter the method. The lock is released when the thread exits the method. This figure illustrates the object's entry set. A thread that tries to acquire an unavailable lock is placed in this object's entry set. A block will be released when the thread owning the lock exits the method. If the entry set for the lock is not empty when the lock is released, the JVM Java Virtual Machine arbitrarily selects a thread from this set to be the owner of the lock. Each object also has a wait set. When the thread enters the synchronized method, it owns the lock for the object. However, this thread may determine that it is unable to continue because a certain condition has not been met. That will happen, for example, if the producer calls the insert method and the buffer is full. So the thread will release the lock and wait until the condition that will allow it to continue is met. When the thread calls the wait method, the following happens. The thread releases the lock for the object. The state of the thread is set to be blocked. The thread is placed in the wait set for the object. How does the consumer thread signal the producer may now proceed? The method notify can be called. So the call to notify, it picks an arbitrary thread T from the list of threads in the wait set. T is moved from the wait set to the entry set. And we can set the state of T from blocked to runnable. T is now eligible to compete for the lock with other threads. Once T has regained control of the lock, it returns from calling wait method, where it may check the value of the count again. Let's take a look of code. On the left side is the insert method. On the right side is the remove method. So suppose the buffer is full and the lock for the object is available. So the producer calls the insert method on the left and see that the lock is available, so the producer can enter this method. Once in the method, the producer determines that the buffer is full and calls the wait. So the call to wait releases the lock for the object, sets the state of the producer to blocked, and puts the producer in the wait set for the object. Now the consumer calls and enters the remove method. The lock for the object is now available, so the consumer removes an item from the buffer and calls the notify. Note that the consumer still owns the lock for the object. The call to notify removes the producer from the wait set for the object and moves the producer to the entry set and sets the producer's state to runnable. The consumer exits the remove method. Exiting this method releases the lock for the object. The producer tries to reacquire the lock and is successful. It resumes execution from the call to wait. The producer tests the while loop, determines that the room is available in the buffer. So the count right now is not equal to buffer size. The consumer proceeds with the remainder of the insert method. If no method is in the wait set for the object, the call to notify is ignored. When the producer exits the method, it releases the lock for the object. A reentrant lock is owned by the thread last successfully locking, but not yet unlocking it. A thread invoking lock will return, successfully acquiring the lock, when the lock is not owned by another thread. The method will return immediately if the current thread already owns the lock. Java semaphore is used to control access to a shared resource that uses a counter variable. Java provides a semaphore class that contains constructors and various methods such as acquire and release to control access over the shared resource. Condition variables provide a means for one thread to suspend execution, to wait, and to notify by another thread by signal method that some state condition may now become true. Java condition variables associated with an reentrant lock. As the number of processing cores increases, it becomes increasingly difficult to design multi-threaded applications that are free from race conditions and deadlock. In this section, we explore various features provided in both programming languages and the hardware that support the design of thread-safe concurrent applications. Transactional memory originated in database theory, provides an alternative strategy for process synchronization. A memory transaction is an atomic sequence of memory read-write operations. The memory transaction is committed if all operations in a transaction are completed. Otherwise, the operations must be aborted and rolled back. The ease of transactional memory can be obtained through features added to a programming language. Consider an example. Suppose we have a function update that modifies shared data. Traditionally, this function will be written using mutex locks or semaphores such as the following. However, using synchronization mechanisms such as mutex locks and the semaphores involves many potential problems, including deadlock. Additionally, as the number of threads increases, traditional locking scales less well because the level of contention among threads for lock ownership becomes very high. As an alternative to traditional locking method, new features that take advantage of transactional memory can be added to a programming language. In this example, suppose we add a constructor atomic S, then which ensures the operation in S execute as a transaction. This allows us to rewrite the update function as follows. The advantage of using such a mechanism rather than locks is that the transactional memory system, not the developer, is responsible, guaranteeing atomicity. Additionally, because no locks are involved, deadlock is not possible. Furthermore, a transactional memory system can identify which statement in atomic blocks can be executed concurrently, such as concurrent read access to a shared variable. Of course, possible for a programmer to identify these situations and use reader-writer locks, but the task becomes increasingly difficult as the number of threads within an application grows. Transactional memory can be implemented in either software or hardware. OpenMP is a set of compiler directives and API that support parallel programming. The hashtag pragmaomp critical, and they're the optional name, which can be used to identify the critical region. The OMP critical directive identifies a section of code that must be executed by a single thread at a time. Functional programming is the process of building software by composing pure functions, avoiding shared state, mutable data, and side effects. Functional programming is declarative rather than imperative, and application state flow through pure functions.